Hello everyone, and welcome to section 4.3, where today we're going to talk about a lot of graphing, how we can use the derivative to draw the shape of the graph more accurately. So we know about the first derivative and the way it provides rate of change information. And we'll also talk about the second derivative and the information it provides for the graph. And we'll use it to get a much more accurate graph just by hand. So in this section, the first thing that we want to do is kind of go back and mention what it means for a function to be increasing or decreasing. So we looked at the derivative, and we saw that if f prime, our first derivative, was positive on some interval, then the graph of f of x must be increasing on that interval. Right? Derivative tells us about rate of change. If it's positive rate of change, the graph must be going up, trending upwards, increasing. If f prime of x is negative on an interval, then the graph of f of x must be decreasing on that interval. All right, so we know these two things already, but just to reiterate them a little bit further. Different marker. So this leads us to design what we call in the math world the first derivative test. And for the first derivative test, we're going to say, let's suppose C is a critical number. F of x. We will say that if f prime changes from positive to negative, i.e. we are switching signs for our derivative, which means we are switching from increasing to decreasing, essentially, then f, our original function, has a maximum, or I should say local maximum, to be more specific, at x equals c. Or I guess you could just say at c, right? And of course, the other way, if f prime changes from negative to positive, then f has a local minimum at x equals c. Right, so c is our critical number. Recall what the critical number means. That's where the derivative is equal to 0. That's a critical number, or where the derivative is undefined. Right? If we can show that our critical number gives us a little bit to the left and a little bit to the right, this type of information, positive to negative, left and right of the critical number, we've increased and decreased, and we've actually hit this maximum. If we go from negative to positive, we had a derivative that was negative, then a derivative that was positive. So we must have been decreasing, then increasing. That means that that critical number C must be providing some sort of minimum. There's one more thing that I really should squeeze in here. Suppose C is a critical number of f of x, where f is continuous at C. Maybe just to make this little extra stipulation, because the other thing that could happen is the derivative might not be defined there. And what's happening is you're probably more than likely ending up with like a vertical asymptote there or something. And so we're going from, a positive derivative over to a negative derivative means we're increasing, but then over here we're decreasing. Well, if there's actually a vertical asymptote there, we can't call that a max. We can't call that a min because there's nothing there. So we do want to be careful. We may come across a situation where if we're dealing with a rational function and we have an asymptote, our function could increase, positive derivative, and then it could decrease on the other side, negative derivative. But you're not going to call that a maximum because the function is undefined there. You can't declare the maximum when there's nothing there to talk about. So we do have to put that little bit of extra stipulation in there. So that first derivative is going to help us graph our function better because we're going to know all the intervals where we're increasing and all the intervals where we're decreasing. And the nice thing is, now we know exactly where to put our maximums and where to put our minimums. When we get those critical numbers and we do that first derivative test, we can see if it increased and decreased, aha, that critical number must be a maximum. If I plug that number back into my original function and get that output, that's where my maximum value lives. And I can put that on the graph. So it's giving us a lot more information now. We can also talk about the concavity of a function, and that is, like the curvature. Is it curving downward? Is it curving upward? And we'll see that the second derivative provides us lots of information about that. So if the second derivative, f double prime of x, is positive on an interval, then my original function, f of x, is concave upward on that interval. And again, since we maybe haven't seen stuff like this before, concaving upwards means upward concavity like this. And then also the other situation, if the second derivative is negative, i.e. less than 0 on an interval, then f of x, well, let's sneak it down here, is concave downward on that interval. And again, when you talk about concaving downward, we mean opens down, right? Bends like this. Now, some functions, obviously, there's a lot more involved. They concave upward, and then they concave downward, and then they concave upward again. Like, look at y equals sine of x, right? That thing just constantly just switches its mind and says, I want to concave up, now I want to concave down, now concave up, now concave down. So there's these points where that concavity can change, right? There's got to be, like, if we look at a function and we graph that function, you can see there's downward concavity over on this side, there's upward concavity over on this side. There must be some point in here where that function specifically changes concavity from concave downward to concave upward. There's got to be a point, that tipping point where it changes, right? And that's the idea, is to find that point. And that's what the second derivative is useful for. The first derivative is useful for finding maximums and minimums. The second derivative is useful for finding that point, which we call an inflection point. It changes inflection from concaving down to concaving upward. let's go ahead and define that officially. A point P is called an inflection point. If f of x is continuous. Again, we do need that continuity. If there's nothing there, then we can't call it a point, right? At P. And the curve changes from concave upward to concave downward. Or changes the other way around, from concave downward to concave upward. And we'll notice when we do some of these, first derivative tests, second derivative tests, you may run into a situation where the second derivative, you set it equal to 0, you see if you have any inflection points, and you might test it and find out that you have concave upward to the left and concave upward to the right. Then it doesn't fit the definition. We can't call that an inflection point. So we want that function to be continuous so that we have that point on the graph. And it does have to change from up to down or from down to up. It needs to change the actual concavity. Then we'll go back and declare it an official inflection point. So again, just to have that picture, kind of drew it and then took it away. If we graph a function, there's some spot on this graph where I'm changing inflection from concave down to concave up. My job is to find that point. Once I've found that point and I've shown that the concavity changes at that point, I can declare that my inflection point, or point of inflection, if you will. And then just because I need more space, get this out of here. And now we can go ahead and declare our second derivative test. So we are testing for concavity for our function. So I'm going to say, suppose f is continuous at P. If f double prime changes from positive to negative at P, then f has an inflection point. At P. And the other way of saying it, if f double prime changes from negative to positive at P, then f has an inflection point at P. Right, so what we want to do is test the function first, see if it changes concavity, and that point P is actually on my graph. Then I can say it's an inflection point. Again, we may run these tests and get concave up, positive second derivative, and then to the right of that point, concave up, positive second derivative. No concavity has changed. That point is not a point of inflection. So, as far as the writing down of the definitions and the actual concepts go, that's that. Now it's time to do examples. Some of these examples can be pretty lengthy because, and you'll see in a second, because as you run through the test, there's a lot of computational stuff that you have to do, and you don't want to mess up something silly like a negative sign because it's going to throw your whole test off. And then you're going to go to graph the function, and you're going to go, wait a minute, this doesn't make sense. How is this function, increasing out to infinity when it's a polynomial and I know it should be decreasing, just based on end behavior. So everything's got to agree. There's quite a bit of computation to do in some of these problems. So take your time with these problems. They can get a little involved. Just really depends on the function and what type of numbers you're dealing with. Okay, so let's see how to use the first derivative test and the second derivative test. And I will try to write a little bit small, not like small you can't see it, but small enough so I can get as much information on this board as possible without having to erase it away. That way you can see the big picture. Let's say we want to find the intervals on which f is increasing and decreasing. We want to find the local max and min values of f. And we want to find the intervals of concavity. That is, where does it concave up, where does it concave down, and inflection points. And we'll steal a function f of x equals x over x squared plus 1. Hopefully that's not too small. There we go. Now we can see that square a little better. So we've got a rational function. The nice thing about this rational function specifically is the denominator is never 0. Right? You got that nice plus 1 there to save you. If x is 0, you still have a positive denominator. If x is positive, well, they're just adding up two positives together. It's getting more positive. If you put a negative value in for x, you're squaring it anyway to make it positive and then adding yet another positive. So the denominator is always positive. You can't make this denominator 0 no matter how hard you try. So that means we don't have to deal with any vertical asymptotes or stuff like that. So it's a pretty nice as far as a first example can go. So first thing on the list, intervals where f is increasing and decreasing. The derivative tells us where we increase, positive rate of change. The derivative tells us where we decrease, negative rate of change. So that's what we're going to go for. We're going to go for finding the first derivative and then applying the first derivative test. So it is a rational function, so I'll use quotient rule. Derivative of the top is 1 times the bottom minus the original top x times the derivative of the bottom is 2x all over the bottom, x squared plus 1, quantity needs to be squared. Before we do this, that's just sloppy. Let's clean that up. We've got x squared plus 1 minus 2x squared. So I'm going to write 1 minus x squared. Right, that x squared minus 2x squared is a minus x squared. So I'm just going to leave it like that in the numerator. Denominator stays, those don't cancel, they're different. So there's our first derivative. Now what we want to do is take this derivative, set it equal to 0 so that we can find our critical numbers. Right, we have to be able to find our critical values. So I have 1 minus x squared over x squared plus 1 quantity squared equal to 0. Again, the denominator is never going to be 0. We can clean this up pretty quickly doing x squared plus 1 quantity squared on both sides. If I multiply that, cancel, cancel. And of course, that's still 0 on the right. So I'm setting the numerator equal to 0, 1 minus x squared. Add x squared over to the other side. That means 1 is equal to x squared. That means that x, if I take the square root on both sides, I have to do plus or minus the square root on both sides. That means I've got positive or negative 1. So these are my critical numbers. I'm going to label them. Now what do I do with those critical numbers? Well, I have to test what's happening to the left and to the right of those critical numbers. If I have a maximum at one of those critical numbers, then I need to see increasing to that critical number and then decreasing after that critical number. Or if I have decreasing, hit the critical number, then increasing, I know I've hit a minimum. Right, but I have to see where it's increasing and where it's decreasing. That'll answer the first question. Then I can go for the maximums and the minimums. So right off the bat, here is the first derivative test. Now, this is how I do it. Lots of people like to do it different ways, but I put a number line down. I look at my critical numbers, -1 and +1, and I put them down on my number line, make sure they're in order. You have no idea how many times I see people write +1 here, then -1 here, and then when they go to graph their function, obviously their number line was backwards, their graph is going to be backwards, or just not make sense at all. So these are my two critical numbers. I put them down. Now I need test points. I'm going to pick -2, I'm going to pick 0, I'm going to pick +2. So those are my test points. You get to choose those, right? Those are up to you, ultimately. You get to pick those test points. These numbers are not really important as far as yielding any information at like maximum or minimum or anything like that. I'm just using -2, 0, and 2 because they're nice numbers. And they're to the left and to the right. Same thing here, to the left and to the right of that critical number, or those critical numbers, positive and -1. So you could pick different numbers like -5, +6, right? You could pick a half, but why would you do that to yourself? Because here's the test. It's the first derivative test. So you're testing the sign of the first derivative to the left of that critical number, in between those two critical numbers, and to the right of that +1 critical number. Notice I'm using my test points in the derivative. I'm not putting -1 in my derivative because I already showed that that gives me 0. There's no reason to redo that. I'm using my test points. So I'll plug -2 into my first derivative. This was like the cleanest version of the first derivative was right here. So I'm just going to hone in on this one. That's my first derivative. Let's plug -2 into it. 1 minus -2 squared up top. -2 squared plus 1 on the bottom, and then square that quantity like that. So I've replaced x with -2, my test point, and now I'm just going to simplify this and see what I get. 1 minus, well, if I square -2, I actually get 4, so the top is -3. -2 squared is 4, but then I'm going to do 4 plus 1, which is 5, and have to square 5, that's 25. I have -3 over 25, which is negative, which means that for me, since my first derivative is negative, my function must be decreasing on that interval. My function spit out a derivative that has a negative sign, anything to the left of -1, that means my function is decreasing on that interval. And again, you can't change unless you're hitting that critical number. And there are no more critical numbers to the left of -1. So it's always going to be a decreasing function to the left of -1. We repeat that process, this time with 0 plugged in, 1 minus 0 squared over 0 squared plus 1 quantity squared. Well, the top's just 1, the bottom's just 1. That's 1, that's positive. Since my first derivative has a positive sign, my first derivative tells me that my original function, f of x, must be increasing on that interval from -1 to 1. I'm hitting 1, that's another critical number, so I'm not sure if I'm changing sign on my derivative. That's why I need another test point out to the right. So we'll plug in 1 minus 2 squared, and again, just going back to this derivative, plugging in 2 for my test point. 2 squared plus 1 quantity squared. So I get 1 minus 4, again, -3, 5 squared on bottom, 25. I'm back to my first derivative having a negative sign over this entire interval, so I'm decreasing from here on out. Now what that does is it helps me pick up the fact that, well, yeah, I've answered the first question like I wanted to, but I've also answered the second question pretty much, almost, because look what happened. At those critical numbers, I decreased, then increased. This has to be a minimum. I increase, hit this critical number, and then decrease. That must have been a maximum. So now I can actually find where these max and where these min values are. Remember, these are just the critical numbers, these are just the x values, but I haven't told them what the maximum value is. I haven't told them what the minimum value the function attains. So I have to go back and hunt for that maximum value. I'm done with the derivative. I don't want to plug this into the derivative because it's going to give me 0 again. I found these numbers to give me 0 for the derivative, so I'm done with the derivative. I want to know what the function attains as far as a value goes. So now I default back to f of x to find that maximum value at +1, to find that minimum value at -1. So I'm having to do the maximum first. That's fine. We'll go back and do the minimum after. We get 1 over 1 squared plus 1, which is 1/2. Yeah, this function's kind of not very exciting. It's got a horizontal asymptote of 0, and then it just kind of around the origin. This function really doesn't do very much as far as like attaining any large values. My minimum. Again, I showed that it happens at -1, so I plug -1 back into my original function to get the minimum value of f. Don't care about f prime anymore. So now I have this nice positive, or I'm sorry, not positive, I have this nice maximum, and I have this nice minimum value that I found. So we've got the first question answered, we've got the second question answered. The third question, and maybe just to, yeah, let's do it up here, just to keep track, because I don't know if I can squeeze it all in on the side there. I'm going to say f is increasing on -1 to 1, and f is decreasing on -infinity to -1, union 1 to infinity, leaving out that gap in the middle. I will say that f has a maximum value of 1/2 at x equals, which one was that, +1. F has a minimum value of negative 1/2 at x equals negative 1. Yeah, that way at least we've got all our information, sort of summarized. This is something I would do typically on a sheet of paper, right? I'd roll through this, roll through my test, even roll through my second derivative test to get everything out of the way. And then at the very bottom of the paper, I would say, conclusion, this is where it's increasing, this is where it's decreasing, this is the maximum, this is the minimum, or even off to the side or something, right? Just to conclude everything in one nice spot. Otherwise, it could be a mess to try and go hunt for, each piece of information. If it's all labeled out there, it's a lot nicer. So I like to do that. I suggest you do the same. Because again, if I can't find it, I can't grade it. Or worse, you go back to check your work, you can't find it, and you can't fix the problem. So increasing, decreasing, done. Max, min, done. Now we need this third one. Where's our concavity at? Let's check that inflection point, or inflection points if we have multiple. So I'm going to stick with leaving the first derivative right there. And we're done with the first derivative test, and we found all the information we can from the first derivative, so I'm going to get rid of that and walk you through the second derivative test. So for the second derivative test, obviously I need the second derivative. So let's do that first. F double prime of x is, again, it's a quotient, so I'm going to use quotient rule. Derivative of the top is negative 2x, right? Just power rule there. Times the bottom. Be careful, there's already a square, so you need that for the bottom. Top, 1 minus x squared. Times the derivative of the bottom. Careful, you need chain rule, right? That square on the outside comes down. You'll have x squared plus 1, my inner function, just rewritten, now to the first power, but then chain rule says multiply by the derivative of the inside, which is 2x. Right? And then the bottom still needs to be squared again, so that's x squared plus 1 to the 4th. Again, I'm not working with that. I'm going to clean that up so I can work with something nicer. So f double prime of x is going to be, I'm going to factor out x squared plus 1 because they both have a common factor of that x squared plus 1. So I'm going to factor that out, and that'll leave me with negative 2x times the remaining factor x squared plus 1 minus 1 minus x squared times, well, that's actually 2x times 2 is 4x. Over x squared plus 1 to the 4th power. Now I can get rid of x squared plus 1 is a factor, x squared plus 1 is a factor, and then just stare at it as a cube factor in the denominator. So that means I'm dealing with f double prime is equal to, here's negative 2x cubed minus 2x minus 4x minus minus is plus 4x cubed all over x squared plus 1 quantity cubed. So now I have negative 2x cubed, positive 4x cubed, that's 2x cubed, and I have a negative 6x when I combine these two. So again, because I'm going to do most of my work over there and I'm done with this messy stuff, then I'm going to go back and underneath where I have my first derivative. And the only reason I'm jumping around like this is because I just don't have the real estate here. Right? I don't have an 8-foot long whiteboard. Wish it was the case. So 2x cubed minus 6x over x squared plus 1 quantity cubed. There. And we don't need this messy stuff anymore. There's no reason for it. It's too much. We've simplified our second derivative. So now I want to go for not critical values, but inflection points. And again, we are very happy that this denominator is never 0. Right? I'm always taking something positive in the denominator, so that's great, which means I don't have to worry about vertical asymptotes or this thing being undefined anywhere. So when I set it equal to 0, the only thing that's going to make this 0 is the numerator. much like we saw with the first derivative. We can multiply both sides by x squared plus 1 quantity cubed and get that to totally cancel. Not that 2 though, that 2 is sticking around. Which means the left-hand side is just 2x cubed minus 6x. Right-hand side is 0. 0 times anything is 0. Factor out 2x, and we'll get x squared minus 2. Or I'm sorry, minus 3. I don't know why I said minus 2. So there's 2x cubed minus 6x, which means we have either x is equal to 0 or x squared is equal to 3, right? X squared minus 3 is 0. I'll add 3, and then I'll say x is equal to plus or minus the square root of 3. Now, I can't jump the gun and call these inflection points because I don't truly know if my function is changing inflection at those points. With the first derivative, when we set it equal to 0, we get critical numbers, period. We call them critical numbers. But when we take the second derivative and set it equal to 0 and get these values, we're not going to jump the gun and call them inflection points until we see that they actually change the inflection of the graph. But everything rolls through exactly the same as it did with the first derivative test. So here is the second derivative test. And it all depends on the problem. Some problems only ask for max and mins and increasing and decreasing. No reason to use the second derivative test. Some problems only ask for inflection points and concavity. No reason to use the first derivative test. Just jump right to the second derivative test. Differentiate again. But most of the problems in most cases are you have to do both, right? They want everything. So again, this is how I do it. Some people like to do it differently. I've got 3 values. I took the square root, so I need positive and negative square root of 3. So I'm going to put 0 in the middle, negative root 3 over here on the left is 0, and positive root 3 over there on the right is 0. So now I have 3 possible inflection points. So I need to pick up some test points. I need to pick up something to the left of negative root 3. Well, negative root 4 is negative 2, so that is a little to the left of negative root 3. Same thing over here. 2 is the same thing as square root of 4. Square root of 4 is definitely bigger than square root of 3. And then in here, again, pick something nice like negative 1, positive 1. Right, so your test points should be in between those possible choices for your inflection points. Make sure you're getting some nice numbers. And again, make sure you put these in order, right? Okay, so now let's go for taking the second derivative and testing it using my test points. Right, so I take my test points and I plug them in. I don't plug negative root 3 or 0 or root 3 into the second derivative because I've already shown that it's just going to give you 0 back. So what I want to do is plug in negative 2 into my second derivative. I want to plug in negative 1 into my second derivative. I want to plug in 1 into my second derivative, and I want to plug in 2 into my second derivative. So in this case, here's what they might say is the cleanest version. You might factor it, but it is what it is. So what we can do is plug all these values into this second derivative. 2 times negative 2 cubed minus 6 times negative 2 over negative 2 squared plus 1 quantity cubed. And then just simplify as best we can, right? Negative 2 cubed is 8, or sorry, negative 8 times 2 is negative 16. This is positive 12. Negative 2 squared is 4 plus 1 is 5. 5 cubed is 125. And again, I don't really care so much that this specific value is -4 over 125. That specific number is not really important to me right now at this moment, or really, almost never really important to me at all. I really just want to know it's negative. That's my goal. My goal is to figure out if the second derivative is negative, then my function must be concaving downward. And again, I like to draw the picture just to help me easily identify where I'm concaving up, where I'm concaving down. And I also like to put the sign in there. That way I'm, twice as sure that I've got the right concavity. Next, we'll test -1. So 2 times -1 cubed minus 6 times -1 over -1 squared plus 1 quantity cubed. Again, we'll just simplify this as best we can. -1 cubed is -1, so this gives me a -2 plus 6 in the numerator. -1 squared is 1, plus 1 is 2, 2 cubed is 8 in the denominator. So this will give me 4 over 8, which is 1/2. Again, I'm not super concerned that it is the value 1/2. I am concerned that it's positive. It being positive tells me that now my function is concaving upward. Positive second derivative, original f concaves up on that interval. Let's keep going. We'll get these out of the way. 2 times 1 cubed minus 6 times 1 over 1 squared plus 1 quantity cubed. That gives me 2 minus 6 is -4 over 2 cubed is 8. There's -1/2. That's negative. Concave down. Positive 2 gets plugged in. 2 times 2 cubed minus 6 times 2 over 2 squared plus 1 quantity cubed. 8 times 2 is 16. 16 minus 12 is 4 over 125. 2 squared plus 1 cubed. That's positive. That's all I care about. Concave up. So now I can see that my function concaves down, concaves up, concaves down, concaves up. So it really is changing concavity at -√3, at 0, and at √3. These values that I found down here. So I am going to go ahead and call all 3 of those inflection points, because I am getting concavity change at every single one of those points. So it wants us to find the intervals of concavity. We can go ahead and mark those down. We've got increasing and decreasing out of the way. We've got max and min out of the way. The intervals of concavity, f concaves up on -√3 to 0, union √3 to infinity, and again, I'm only erasing as I go because I'm pretty much out of space here. F concaves down on -∞ to -√3, union 0 to √3. So that takes care of my concavity. Increase, decrease, max, min, concavity. I really need to label those inflection points as points, right? I need an x and a y value. So I can say that f has inflection points. -√3, comma, I don't know the y value, right? I have to go find that y value. 0, comma, again, I don't know that y value. I have to go find it. And √3, comma, again, I don't know that y value. I have to go find it. So what that means is we're pretty much done with all this derivative stuff. The only thing we need to do is go back to our function our very original function, I don't want to plug these back into the derivative or second derivative because it's just going to give me 0, right? So I want to go back and plug those values into our original function so I can finish labeling these points as ordered pairs. So my job is to now find f of negative root 3, f of 0, and f of positive root 3. So that I can finish labeling those points as points, right? They're not points if they don't have an x and a y value. So let's go and get it. Negative root 3 over negative root 3 squared plus 1. That's negative root 3 over, if I square this, I just get 3 plus 1 is 4. Perfect. Negative root 3 over 4. Sorry for mixing up the colors there. 0 over 0 squared plus 1. That's just 0. So we're at the origin. 0, 0 is an inflection point. And then positive root 3. Again, I'll square that to get 3 plus 1 in the denominator. So I just get root 3 over 4. And now we can put that final check in there. So when looking at this function, now you have a lot of information at your disposal. I mean, I warned you, I said these problems are, can be pretty lengthy. So it takes a little while to get through a lot of the stuff. But now you've got so much information at your disposal. This, if you just go back and look at the horizontal asymptote, you can see that the degree of the top is less than the degree on the bottom. So it does actually have a horizontal asymptote of y equals 0. Which is why I said, this function doesn't really do anything crazy. It just kind of rides along. And then we can see that it hits a minimum at negative 1. And the minimum value that it hits isn't even that crazy. It's just negative 1/2. So I'm hitting a minimum value basically right there. And then over here at positive 1, again, I'm not going too crazy. I'm only getting a maximum at 1/2, right about here. And I know I'm increasing from negative 1 to 1, and I'm decreasing everywhere else. So I know that my function is going to be decreasing, hit that minimum, increase, hit that max, and then decrease again. But before I do that, and just do that like simple curve, and risk drawing it like a straight line here, it's not a straight line because we're also looking at concavity. This thing has 3 inflection points. One of them's right at the origin. The other one's at negative root 3 over 4. The other one's at root 3 over 4. So root 3 is if you look at it, it's like 1 point something something, right? Because root 4 is 2. Root 3 is like 1.7 or something like that. So it's pretty close right around here. Pretty close tucked in right around here. Now I can actually get a nice visualization for my function. It comes in, it's concaving down, hits this, still concaving down, but then it starts concaving again, comes up, hits a maximum. So at each one of those points, I've got to change concavity from down to up, and then from up to down and down to up again. Yeah, so again, not the best graph. It didn't ask us to graph it. We're so squeezed in here with this really, really tiny values that we have to deal with. But you can see how it just provides so much more information for you in order to get the graph sketched. But like I said, this function doesn't really do a whole lot unless you're living very close to the origin. So that's kind of hard to graph as is. So let's take a look at another example. Where this one says, find the intervals decrease, and decrease. Find local max. And min. Find the concavity and inflection points. And then this one tells us to go that extra last mile and sketch the graph. So the function they will give us is f of x is equal to 36x plus 3x squared minus 2x cubed. So this is the function that they give us. And right off the bat, just because it's not actually in like descending order, I'm going to rewrite it. Negative 2x cubed plus 3x squared plus 36x. Why would I do that? Well, it's just easier on the eyes for me. But also, right away, I can tell this is cubic with a negative leading coefficient, meaning it's going to be reflected and it's going to come in, have at most 2 turning points, and then go down. So I can already tell it's going to decrease here, maybe increase if it turns, and then later it's going to have to decrease when it's all said and done. So I already start to know the behavior, which means I'm already checking my work before I even get to the first derivative test. So that's, in my eyes, that's very helpful. So we want to go through all this stuff again. Need that first derivative to do the first derivative test. So we'll get negative 6x squared plus 6x plus 36. Our goal is to set that equal to 0 to get our critical numbers. I'm going to factor out a negative 6. And the only reason I'm going to do that is because I'm going to be left with a quadratic that I really do want to factor and get those zeros. So I factored out a negative 6, which means I change those signs as well. I can divide both sides by negative 6. It's not going to contribute anything to me finding critical values. And then I'll factor that x squared minus x minus 6 to get x minus 3 and x plus 2. So I have x equals 3 or x equals negative 2 as my critical numbers. So those are my 2 critical numbers. I need those critical numbers so that I can then run through my first derivative test. Here's my first derivative test. I am going to take my number line. I'm going to take my critical numbers. One is negative 2, one is positive 3. I'm going to put them in the correct order, left to right. And I'm going to pick on some test points. I think for test points, 0 in between them is a great number to use. 4 is a good number to use on the right, and negative 3 is a good number to use on the left. I'm picking some nice integer values, small integer values. And then I'll just test them. So I'll look at my first derivative, and I'll find f prime of negative 3. I'll find f prime of 0, and I'll find f prime of 4. Hopefully that is not too squeezed in down there. It's a little tight, but we're just checking f prime of negative 3 for its sign. We're not even really explicitly looking for a specific number. We're just looking for positive or negative. So I'm going to go back to my derivative. I'm just going to start plugging things in. In this case, I'm going to look at the one with the negative 6 already factored out. I'm going to say negative 6 times, and then I'll start plugging in. Negative 3 gets squared minus negative 3 minus 6. Again, I'm only concerned about the sign. So I have a negative 6 being multiplied by, this is 9, plus 3 is 12, minus 6 is 6. So negative 6 times 6 is negative 36. Again, I really just care that it's negative so that I can say I'm going to decrease until I hit that first critical number, negative 2. Then we'll plug in 0, negative 6 times 0 squared minus 0 minus 6. Again, I'm doing the factored version. So this will give me negative 6 times negative 6, which is positive 36. Again, positive means I am increasing. So what that means is one of these critical numbers, in this case negative 2, has got to be a minimum value. Or that's where the minimum value must occur. And then we'll plug in 4, negative 6, 4 squared, minus 4, minus 6. So that will be negative 6 times, there's 16 minus 4 is 12, minus 6 is 6. We get another negative 36. Negative, so it's decreasing. Which means this positive 3 critical number must be a maximum. See how it increased then decreased? I must have found a maximum there. So again, lots of good information. We know where the min and the max occur, but we don't know what those min and those max are. So to find the minimum, I would need to plug in the value negative 2 because that's where it happens. But I don't plug it into the derivative because obviously I'll just get 0. I plug it back into the function to see what I get. So let's plug negative 2 into our function. F of negative 2 is going to be, and I'll go back to the very original, 36 times negative 2 plus 3 times negative 2 squared minus 2 times negative 2 cubed. So this gives us negative 72. That'll be positive 4 times 3 is plus 12. That'll be negative 8 times negative 2 is positive 16. Just so we don't risk messing this up. Get negative 44. So I plug negative 2 in to my original function and just crunch it, see what we get. If you have this function already plugged in your calculator and you just want to go to the table, that's the best way to do it, right? F of, what else do we get? Maximum at 3. I'm going to plug in that f of 3. 36 times 3 plus 3 times 3 squared minus 2 times 3 cubed. That will be 108 plus 3 squared is 9 times 3 is 27 minus 3 squared is 27, and then 27 times 2 is 54. So 108 plus 27 minus 54 is 81. So I want to make sure I get those numbers right. Now, again, short on space, but at least we're done with intervals for the increasing and decreasing, and we found those local max and those local mins. So I'm just going to sort of summarize here like I did with the last problem. F is increasing on negative 2 to 3. So between those critical values, I'm increasing. F is decreasing on, and then careful, there are two of them, negative infinity to negative 2, union 3 all the way out to infinity. We can say f has a local min at, and this time I'm just going to write the point, negative 2, comma, negative 44. And f has a local max at, and again, I'm just going to write the ordered pair, 3, comma, 81. So that gives us all the information that we need from the first derivative. And then I'll give myself some space back here. So now we need to move on to the concavity and the inflection points. So I'm going to keep that first derivative there. There was our first derivative. I'm going to take away the equal 0 because we're done with critical numbers. And I'm going to use that first derivative to get my second derivative to see if I can pick up some inflection points and talk about concavity. So f double prime is going to be negative 12x plus 6. So since it's a polynomial, it's only getting nicer the more we differentiate. I want to set that equal to 0. I'll factor out the negative 6. Now it'll give me 2x plus 1, or sorry, minus 1. All right, there's negative 12x plus 6. So I just factored that out. So the only thing that's going to make this 0 is if 2x minus 1 is 0, which means x equals 1/2. Add the 1, divide by 2. Now, I don't exactly know if this is an inflection point just yet. If it is, great. If it isn't, also great. Like, who's to say? So I need to do my second derivative test. So that means I'm going to draw my number line. I only have one number to put down, and that number is 1/2. But I need to test to the left and to the right to check for concavity, because obviously I have to give them the concavity. So again, I'll pick 0, and I'll pick 1, some really nice numbers. And I'll test them using the second derivative. So f double prime of 0 and f double prime of 1. Again, second derivative test. So I'm testing the second derivative, which means I go back, and it doesn't really matter, but I'll use the factored form again. Will give us the same information. Negative 6 times 2 times 0 minus 1 is equal to negative 6 times negative 1 is positive 6. So I know that I must be concaving up, since my second derivative is positive on that interval. And then plugging in 1, negative 6, 2 times 1 minus 1. Well, that is negative 6. 2 minus 1 is 1, so that's definitely negative. So I'm concaving down, which means, yes, this is an inflection point. I've changed from concaving upward to concaving downward at that x equals 1/2, so I definitely change inflection, so I call it an inflection point. So again, we have the intervals for concavity, and we found where the inflection point happens, but to label it as a point, like an ordered pair, I'm going to have to go ahead and find the y value. I'm going to have to go back to f and plug in that 1/2 value and see where the inflection point actually happens for the x and y coordinate. So I'm going to do 36 times 1/2 plus 3 times 1/2 squared minus 2 times 1/2 cubed. So there's 18. There's 3 times a fourth, that's 3/4. Minus, there's 2 times 1/8, which is minus 1/4. So this is 18 plus 1/2. Right? 3/4 minus 1/4 is 2/4. Common denominator means 36 plus 1/2, 37/2. So that's the y value that corresponds to this x value. Again, notice I went back to the function because I'm finding the actual y value. I'm finding f of wherever this inflection point happens. So, summarize it up. F concaves up on negative infinity to 1/2. F concaves down on 1/2 out to infinity. And then we'll jot down our inflection point. Hey, I can remember that number, right? Oops, I already forgot it. F has an inflection point at 1/2, comma, whatever that number was. No, I'm just kidding, I remember. 37/2. So the last thing that it asked us to do was sketch. Whenever you see this word sketch the graph, I am not looking for absolute perfect graphs with everything under the sun labeled on top of them. They can get a little messy if you start doing that. Like, here's all the zeros, here's all the max and mins, here's all the inflection points. If you try and label absolutely everything on that graph, trust me, there is way too much information to put on that graph, unless it's a boring function. So when it says sketch the graph, I err more on the side of just give me a sketch, like it says. Give me a basic shape. Make sure your max and your mins are relatively close to where they need to be. Make sure your inflection points are actually changing the inflection of the graph. Don't just graph something concaving up and then curve up again. Right? If it tells you to concave up and then concave down, I want to see that you change that concavity somewhere near this point. Right? So again, for me, when I say sketch the graph, it really does mean you're doing it by hand. Just give me a sketch. I'm not looking for the best artist in the world. I'm just looking for a rough sketch. Right? We have plenty and plenty and plenty of graphing utilities and computer software to graph these things. Right? And they graph them quite perfectly. If you're doing it by hand, there's got to be room for a little bit of error. So we've got all the information. Now, look at your information because I've got to somehow get this maximum in here, and it goes all the way up to 81. And I've also got to somehow get this minimum in here. It goes down to negative 44, right? So don't just do like 1, 2, 3, 4, 5, 6, because then you'll never get this point 81 on your graph, right? It's just not going to fit. But as far as left and right, like x values, I don't really have to go that far. So I'm going to draw it, but I'm going to draw it with a sort of a weird scale, like there's 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. But then for my y values, again, I've got to get up to 81. So I'm going to do 10, 20, 30, 40, 50, 60, 70, 80. And then down here, I have to do 10, 20, 30, 40, 50, 60. Yeah, I only need to go down to negative 44. So I'm okay there. So again, watch your scale because you may need to do some adjusting depending on what you have. Okay, so increasing from negative 2 to positive 3 out here, which means I know my function is going to be growing. Let's get those max and mins down so that I can show where my function is decreasing, increasing, decreasing, and hit those max and mins. The minimum is at negative 2, negative 44, 10, 20, 30, 40. So I'm going to have to go a little underneath that, almost halfway. There's my minimum. Then I have 381, so I have to go out 1, 2, 3, and then all the way up to 81. So I'm going to be way up here. Right, and I'm putting max above that so I know not to go higher than that. I'm putting min below this so I know not to dip below that point. So I've got those points in roughly the correct spot. I'm not going to increase to hit this. I know it's a minimum, so I'm going to decrease, increase, decrease. But before I get to that, I know I have to change inflection at 1/2, comma 37 halves. 37 halves is like 18 and a half, or not like 18 and a half, it is 18 and a half. So it's going to be roughly around here. Here's half. Roughly right about here is 18 and a half. So there's my inflection. So I'm going to concave up while decreasing. Then I'm going to increase but still concave up. Then I'm going to switch to concaving down while still increasing. And then I'm going to concave down while decreasing. So again, need to hit this minimum value. Need to hit this maximum value. And I want things to be sort of smooth. Need to come here but increase, concave up, which means this is going to concave upward, and then concave downward, still concave downward, and again over here, concaving upward. So lots of upward concavity all the way to 1/2, lots of downward concavity all the way to 1/2, check, check. There was my inflection point. There's my max and my mins, those are on there. And then, of course, the increasing, does it line up? Yeah, -2 to 3, I'm growing. And outside of that, from -infinity to -2, I'm decreasing. From 3 to infinity, I'm decreasing. So everything lines up, everything agrees. That is what I call a good sketch of a graph. Right? Okay, so again, that's only 2 examples. You can see these examples do take some time, so practice them and be patient. Do not rush this stuff. If you try and rush something in this whole process, you're going to miss a negative sign and it's going to ruin everything, right? So take your time with it. There's no other way than to just take your time, be patient, and make sure you're getting all the correct values that you need. Like I said, if it's helpful to you, which it's very helpful to me, write everything out, like conclude everything that you found. As you go through and do your work, you might take up the entire page and need to use the back or a separate sheet of paper, right? Do everything, but as you find all these things, have a spot dedicated on either like the side of the paper or at the bottom of the paper where you're just going to put all your conclusions. That way, when you do go to sketch the graph, you don't have to hunt through all your work to try and find out where was that minimum again? I know I found it. Where did I put that minimum? If you label it at the end or off to the side, you can just quickly say, okay, now I have to sketch the graph. What's my minimum? Oh, there it is. It took less than 1/2 second. So the neater you are and the more patient you are, and yes, it's going to take a little bit more time to get through all the work, but in the end, it saves you that time back again. Whereas if you're just messy, I found everything, it's all there, it's on the page, just I don't know where it is, but now I have to go back and look for it. It's going to take you twice as long to look for it. So again, just some personal advice there as far as trying to be organized. The more organized you are, the better it is. So that's 4.3, and we'll see you for 4.4.